Okay, I guess we can start. Um, so basically, what I'm going to tell you about today, is one of the possible decompositions for a tensor you can do, um, which is going to be called like the tensor train decomposition. So, it is also called the matrix product states. So if you write it, yeah, tensor trains. So usually you may see them referred as TTs, like tensor trains. The other name for them is like the matrix product states. Another name. And if you call them that, they usually go under the name NPS. Okay. Um, so the idea is that when you have tensors, they they are they don't have as many nice properties as matrices do. So, like the operations that you can do on them, there are more options for what you could do. So you'll see today that the way that this decomposition works, there's more than one way to do it. Um, and there are actually other types of decompositions out there. So this is not the only way to decompose a tensor, but it is like this particular one that I'm going to tell you about is like a very advantageous one, um, because of how it's like if you think about it from a data perspective, because of how it stores like the data. Maybe if we have time, we'll talk about that today. If not, I'll tell you about on Thursday, like some of like the advantages of like using this particular technology. Um, but yeah, like so it's not going to be unique, at least I'll say that for now, and you'll see why it's not going to be unique in a moment. So it's not, there's going to be more than one way to do it. There's will be so but in a nutshell, what's going to happen is that we're going to have a tensor. Like I'll just kind of like verbally say the steps, and then we'll kind of like write in some more of the details. But kind of like the main idea is you start with a tensor, you will turn it into a matrix, okay? Uh, and again, the way in which you turn it into a matrix, there are many options to do that. That's where like the non-unique, that's where like the non-uniqueness starts coming up. Uh, then you apply everything to that matrix. I'll remind you about SBD in a moment, but um, once you have SBD, you kind of like keep, if you think of the SBD as it decomposes the matrix as a product of matrices, right? So basically, you kind of will keep one of those factors, and then the other one gets retensored. So you keep one of the factors, and the other gets turned into a tensor, but of one fewer leg or one fewer index, and then you kind of like reiterate the process. So it's kind of like a recursive thing. So. Um, So so you keep one of the factors, one of the factors, and and the other is turned into a tensor of a fewer index, one fewer index, and then you repeat, okay? And the other is turned into a tensor with a fewer index. And yeah, just to kind of like keep the diagram, like then you go back to where you started, right? Because now you have a tensor, but now that's usually why it's turning, right? Because you kind of like keep moving one leg at a time. Um, so again, you'll see it. Like, it's like a very clever way to do it. It's very nice. But it does have like many advantages, even if it's not like a unique way to do it, but still like a useful thing. Once we have done, so basically, yeah, they give like people enough that we can go through all of it today, and then on Thursday I'll do some examples, show you how it looks like, comment on some of the advantages that it has, and then like next week we can continue some applications where you kind of use a tensor that that's what change the composition for certain problems. Okay, so let's talk first about how is it that you can turn a tensor into a matrix. Again, there are many ways to do that, but one of the ways to do it is called the tensor unfoldings. So I'll tell you tell you about that with an example, because once you see an example, you'll see that it's kind of like pretty natural. Oops. So it's going to be the mode and unfoldings. That's how this is called. Okay, so just to have something concrete that's easier to keep track of, I'll have almost like a very small tensor that we kind of like can write everything down. So I'll have a tensor. So here's an example. I'll have a tensor Tijk. So it's going to have two inputs, and just to have like some small numbers. I can only take two values. So I is going to be 1 or 2. J could take 3 values, 1, 2, 3. And K could take 4 values, 1, 2, 3, 4. So I'm also putting like different sizes so that it's kind of like a bit easier to keep track of. So, in totality, right, like the tensor will have 2 times 3 times 4, so that will be 24 entries, right? So this is a tensor with 24 entries, right? And so because it's kind of like three-dimensional or like with three legs, you can even think about it kind of like rectangular, like a box, right? So you could try to even draw like a picture, like for it. I'll think the way I'm going to think about it. I mean, I'm not going to work with a 3D picture because it's a bit too inconvenient. But imagine kind of like there's like a front face and a back face. That would be my eye. So and then and J and K will be kind of like the row and the column. So like just to kind of like be more clear, like J goes down in this direction, K will move to the right, and I will go kind of like in this way. So I'll call so you can think about this tensor as kind of like two matrices. One, like the front matrix and the back matrix. So the front matrix is going to be related to I equals 1. So that's going to be you can call it like the first page if you think of the tensor kind of like as a book or something like that. So, or like a document. So or like the front matrix, let's call it. So I equals 1 represents the front matrix. And I equals 2 is going to be the back matrix. So, and again, I'm going to just put like some concrete entries so that we have something to look at while we do this. So I'll say that the first page or the first matrix is going to be, the entries are just going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12, 13. So I'm putting like a different number for each entry because that also kind of like, it makes it easier to keep track of how you're going to turn it into a matrix. Otherwise, it's a bit like, if there were some repetitions, it's less clear, what you're going to be doing. And oops, let me just also write this. I'll write them here so that we can also refer to them more easily. And I'll try to, on MATLAB and on Python, there's ways to do the unfolding. So I'll probably have an assignment, or you just kind of experiment with the tensor, like turn it into different unfoldings, and maybe kind of see how it turns out. Like, there are different conventions for how to do this, but do something like that so that you can kind of see like numerically how the decomposition comes. Yeah. Okay, so what did I do? Did I start something for or oh no, it's 4 columns. Yeah. So it's like, yeah. So because it's 1, 2, 3. So again, J, right? So J is the number of rows for each matrix, and K is the number of columns for each matrix. So yeah, there are 3 rows and 4 columns, right? 3 rows, 4 columns, and 2 pages or 2 matrices. So that's one way to, to think about this tensor. So I'm kind of like putting like an arrow just so that, is that use like the usual notation from linear algebra is that instead of like I, J, and this big A, and but all that, there's not that. Okay. So again, there are many ways to, turn this into, like, if you think of the tensor being defined by these 24 entries, what I'm going to do is like, there are 3 unfoldings, that's what their name is. There are 3 unfoldings that we will use to turn it into a matrix. So I'll show you first like the mode 1 unfolding. So that's going to be how it's called. This is also the easiest to keep track of. Okay, so the idea of the mode 1 unfolding is that if you think of the indices of the tensor as being I, J, and K, right? You got 3 indices. So in the mode 1 unfolding, what you take is the first mode. First mode is kind of like just a way to say that that's the first index. So you take the first index, which in this case is I. I don't keep that as its own index, but you merge the other 2 kind of as a new index. So you take J and K, you can merge them as a single index, which I'll just call J. So So I'll put them kind of like together in a pair, just to kind of like indicate that I'm thinking of this as kind of being like just one piece, and I'll show you how it's supposed to work. It's kind of very natural, but you just have to see it with an example to convince yourself that it kind of makes sense. Because if I write down the formula, like the formula for like, obviously there's like a formula for how to do the mapping, but it's a little bit too It's just better to see with an example how it's going to work. Okay. So in this interpretation, again, this was a 2 by 3 by 4 tensor, right? Because 2 entries for I, 3 entries for J, and 4 entries for K. So in this way, it's going to become a 2, right? And then 3 times 4 is 12. So from this perspective, this is going to become a 2 times 12 matrix. Okay, so it's still not same number of entries as you can see, right? And the way to do this is that I is the first entry, and sorry, the first index. So I is now going to be the row, represents like the rows, keep track of the rows. So this matrix is going to have 2 rows. And then basically for the other 2, what you do is kind of like increase first the J, and then you increase the K. So let me see. So what will happen is that I is the row index for this matrix, and then you increase J first for the columns. For the columns, you increase J and then K. Okay. So let's see what this means. So again, it's going to be a 2 times 12 matrix. So it's going to be a 2 times 12 matrix. So on the first row, because that's the index I, right? So on the first row, it's going to be the first, like the stuff that appeared on the first page or like the first matrix, right? So this is going to be the index for the front matrix. And the second row is going to be the stuff that appeared on the back matrix, right? So let's just think about what this means. So for example, if you look at the first row, right? For the first row, then I is 1, right? And then you start giving values to J and K. So you start with the smallest values for J and K, which would be 1 and 1 for each of them, right? So that would be the first pair. Okay. So you have to identify what is the entry 111 of this tensor, which is just 0, right? Like first page, first row, first column, so easy, right? Okay. Then you move to the next entry. So again, we're still looking at the stuff on the front matrix. So like index I equals 1. So the next one would be, let me use a different color. Once you see how it works, like with a few examples, then like you kind of believe what's going to happen next. So the next entry would be 1, right? Like it's still with I equals 1. But as I was saying, you increase the J first. So I'll increase J first. So I can increase J up to 2, right? I got to, okay. So increase J to 2, and I'll keep K being 1 first, because I'm increasing J first. Okay. So you have to say, okay, what is 1 to 1? So again, you look at the front page, you look at the second row, and then the first column. So that is like the 4 here. Yes. Yeah, well, yes, this is the MATLAB convention. I believe in Python they go row. I mean, they go in a different way. Yeah, but like like you have to make a convention. That's what I was saying. Like there are different alternatives. But the way I'm doing it, because in some of the literature they tend to go this way, but it doesn't matter in the end much, you know. But you just have to make a convention, you know. So, but is that make it up for everyone? And then you just well, I won't bore you. I'll just do the next one, and then you kind of like you'll see that how it went. So, and then the next one would be, you know, right, 1, 3, 1, right, and that would be yeah, like first page, third row, first column, and that would be the 8th. And then yeah, I'll just put I mean, it's a fun exercise to do it yourself to, you know, convince yourself that this is working the way it's supposed to. But then it would be 1, 5, 9. Right. So yeah, now you move to the second column, right? And then the third column, and then the fourth column. Then 2, 6, 10. Oh my God, I don't have space. 3, 7, 11. I should have like let me write them again with like a less space in between. Right. So, but it's right in at least along the mode 1, you know, that's why I want to show you how it looks like for all of the 3 modes. But at least along this first mode, it goes like in first, you kind of like 3 columns to the first column, then the second column, the third column, and then the fourth column. And then you do the same for the other page, right? So it would be 12, 16, 20, 13, 17, 21, okay, 14, 18, 22, 15, 19, 23. Okay. And yeah, that has the same number of entries. And hopefully it's possible to imagine that this is like a reversible operation, where like if I had, you know, we started from this matrix and I ask it, you know, turn it back into a tensor of 2 size 2 times 3 times 4, you know, then you know, you can kind of like go backwards. So this is kind of like maybe a bit easier to go from the tensor perspective to the yes.
So are we losing the order? We're losing the order of the original tensor, right?
Sorry?
We're losing the order of the original tensor, right?
Yeah, you're losing right, like you're losing the order of the because you turn I mean the only thing that's preserved is the number of entries, right? Like the number of components, right? But like you know, you can even do something more extreme, which is called like the vectorization, as you know, where it's just turn a tensor into a vector. That itself is not that useful, so that's why like you know, but that is like even more you know extreme version of that, right? But yeah, like the number of indices, right? No. Um, like in fact, if you had started, I mean, like if you had started with like a higher order tensor, like you know, you could have started with something with 4 indices, and if you do the same, I mean, you could have done something same where like you keep this one as the first index, and then the other 3 are merged into a single index, so that would have gone from 4 indices to 2. So in this matrix, I don't know, we're not the word, but it's matrixization or like, you know, turning it into a matrix. And you know, if you guys started with something with 10,000 indices, you know, converts it into 2 index things. So it is like a, you know, it's a big collapse, but kind of like in the number of indices, which is similar to oh yeah, it's kind of yeah, I think I mean I think it goes under different names. So yeah, you may have similar for that. Or is there the order? Well, let's see. So I have to check what they do. I mean, but floodplaning is definitely a phrase that they use like for conversion, but yeah, I don't know if they. Yeah, I just want to just sticking with unfolding, but yeah, like there's a lot of different like tricks and you know, yeah, but it's like a particular version of that, you know. But yeah, it doesn't preserve that's like the order. Yeah. But it's still useful. You'll see that it's actually like a very useful thing. I don't know what to really think about. Like, right, it is going to be like, I mean, basically, well, just kind of like give you like a heads up, like you know, the idea is that it kind of like when you do the tensor train decomposition, if instead of like you know, like if it were all like if it were something like, if it were like kind of like a cubicle box, right? If you had like, I don't know, like what, let's say like you had something like, with n indices, but all two entries. Well, like it's instead of exponential storage, you just need like something that's linear in the number of like entries. Like that's kind of like the idea. Like you'll see why, once I write it down. Um, and then the other two unfoldings are kind of like the same. I'll just mention them quickly so that you see, but that you have to be careful when you read them. You do have to think about what you're saying. Let me just copy paste this picture again. Right. So for the mode 2 unfolding, you take I, J, and K, right? Mode 2 refers to second index, so it would be J, right? So now J becomes the first index, okay? And then just imagine, erasing J from here, so you're left with IK. So I'll just read it off as I, comma K. Okay. So again, this would be 2 by 3 by 4 tensor, and it's going to turn into, it's going to be turned into what matrix? 3 times 8 matrix, right? So that was, and again, for a fixed J, you increase the I first, and then you increase the K. So that's how I'm kind of always reading it. So for fixed J, increase I first, then K. Okay. So how does this look? Again, it's supposed to look as a 3 times 8 matrix. So the J becomes the first index. So it's still kind of like a row index. So like there were 3 rows. So like this is still kind of like the stuff that appeared on the first row, the stuff that appeared along the second row, and the stuff that appeared along the third row, right? Okay, but like for example, now, right? So again, you can kind of like start still with, just so that you see the difference. Like you do like 1, 1, 1. But now what does this mean? This means we will go to the first row, go to the first row, go to the first page or the first matrix, and go to the first column, which is still going to be the same thing as before, but now you'll see like the difference in the next one. Okay. So for the next one, again, you keep the row index fixed, right? Which was J. So it's the next one would be 1, comma 2, comma 1. So what does this mean? It means go to something on the first row, which is on the second matrix, on the second page. But now you have to go to the back matrix, because again, this is I was the page index, and then go to the first column. So you go to the back matrix, first column, first row, that was 12. Right. So it's kind of like zigzagging now between the different pages. Right. And like just to kind of do the next one, it would be what? It would be 1, that is the I was okay. I was only 2 values, right? So now it kind of like it sets, right? So like now you start increasing the the case, right? So this would be, go to the first row on the first page on the second column, which would be 1. Right, so after you increase I the most that you could, you kind of like reset everything, kind of like restarts the cycle. So now it gives you this one, and then you kind of like alternates again. So let me put this here. All right, so the next one would have been this one. So let's, sorry, I'm not writing them here. So yeah, once you understand kind of what it's doing for the first few cases, you kind of like see what you should do for the others. For example, back and forth, back and forth, back and forth, back and forth. So the other two would be 214, 315, right? And the others like kind of look the same. So 416, 5, 7, sorry, 5, 17, 6, 18. That's why it was useful to give different entries to everyone. So here to keep track of.
It's nine of these example all the numbers are reconstruct the order of the tensor, taking out all the numbers.
Let's see. Oh, like, like you're saying if you knew, right, because you always, in the first mode, like, the row index from each of the matrices is always one of the, the number of entries of one of the indices, right? So like, yeah, like you could be able to read off the order. Yeah, because like the first, like, if you have said that this one has a N1 entries, this one has N2 entries, this one has N3 entries, and so on. Then, you can read off like the numbers N1, N2, and 3 just from like the number of rows from which you will make readings to change, if you change it for So yeah, that would be allowed, that would allow me to read it back. I mean, obviously, from our perspective, we're starting from the center already, so it's not like an issue for us, right? But yeah, if someone were to tell you, here are like the 5 possible modes, right, of a tensor. But the moment you say also there's like 5 like the way I'm doing the unfolding, right, there are only 3 possibilities, right? So like the moment I tell you there are 5 possibilities, it's already kind of baked in that it's another 5, you know what I mean? So that's why, you know, not that it's hard to go back and forth, but like these two person. He said that they aren't, that it requires conventions, right? There's not like a canonical way, there's not like a unique way to kind of like turn the tensor into a matrix, right? But it's not an issue for what we want to do it for, right? And yeah, like, just the last one, like, well, hopefully, just to show you, like, the last one, it's kind of like the same idea, but I'll just write it down here. So the mode 3. In the mode 3, you just unfolding. Now the last index becomes the first, right? So it's K. And then it's again, it's kind of like imagine erasing it. So you just get I and J. So it's kind of like the same for fixed K, you increase I first. For fixed K, increase I first. But then this was like again, because it was 2, because this one was 2 by 3 by 4, then this one would become 4 times 6, right? So it would be now like a 4 by 6 matrix. And now kind of like the column index becomes a row index, right? Like it's kind of what's a little bit confusing when you do it the first time, because like you do have to be careful, not, which is good that, you can just use like a Python code or like MATLAB or whatever you want just to do it, because it can be a bit like confusing to kind of like just turn in your head like the columns into rows. Like, every time you do it, like it does require some, right? Because then now this is column 1, this is column 2, this is column 3, this is column 4, right? Like that's now the rows like going down of the column, right? And then and yeah, like again, like I'll just do 3 of them, like kind of like again, like so the first 3 would be what, for example, it would be 1, 1, 1, right? Which is always the same, right? It's the 0. but then it would be 1, 2, 1, right? And so what does this mean now? It means column 1 on the second page, and then on the first row, so like 12 here. Okay, but then, okay, and then in a sense that does start like the other one, right? Like the other one does start at 0, 12. But now for the next one, I think you should see like the difference, right? Because if you do the next one, you do now again, it resets itself. So it's still on column 1. It's column 1, page 1, column 2. It's column, sorry, row 2. Column 1, page 1, row 2. So it's a 4, 12. Yeah, no, it's fine. And then the others kind of like go in this, and then you kind of like keep, you do the rest once. I mean, it's kind of like fun, but again, hopefully, like you can just do them like on a computer. I'll make sure to put like an assignment or something like that so that you can experiment in fun how. Okay, so that is, but I did want to show you like the how the three unfoldings look so that you don't think, oh, you just flip out to the problem first. Like, it does really, you have to understand what is becoming the first thing that once you understand it, then like kind of like the convention is pretty clear, like, how the reading should go. Okay. Okay, so that's the first thing I wanted to say. It was a little bit of notation or like, a simple like operation, but it's not like people to know. Now, just as so we have talked about the SVD, so I'll just remind you. Oh, actually, I should say something about, another thing about that's useful about the SVD, which I don't know if I had said it like explicitly, but let me just mention this because it will be useful for something that's called like the truncated SVD, which is kind of like the same, but you'll see why it's convenient as well. Well, let's just talk about SVD and truncated SVD. And I'll use it like for the tensor trains, like what I'll use is a truncated SVD. You'll see why in a moment. But just to remind you, basically the idea is that you had like an M by N matrix and you write it as U sigma V transpose, right? Where this one was M times M. The sigma matrix was M times N. And the V transpose itself would be what, N by N, Um, and the U and the U and D, those two matrices are made out of like the eigenvectors for like, either A transpose or A transpose A, right? So I'll just say that U and sigma, sorry, U and V are matrices of eigenvectors, right? And sigma, as you remember, like is mostly, bunch of zeros mostly, except for like some mini diagonal where you have like the non-zero singular values, right? And then there's kind of like zeros everywhere. So sigma 1, sigma 2 up to sigma r, right? Where r is the rank of the matrix. So r here is the rank of A. And yeah, sigma 1 is greater or equal to sigma 2, greater or equal to sigma 3, greater or equal to sigma r. And this one, I'm just referring to the strictly positive singular value. That would be the decomposition. If you write this in terms of the tensor product, right, like the SVD, it's kind of like nice to write it in terms of the tensor product because gives you a different perspective, right? So from the tensor product notation, A is the sum from 1 equals R, uh, I equals 1 to R of sigma I UI tensor BI, right? And here's like something, again, I don't know if it's like explicitly, but of course, LVD decomposition has lots of nice features, which is makes it worthwhile. But even if you just look at it more like at a storage perspective, of like let's store the matrix, um, let's just to make this a little bit easier, like if say the matrix had been a square matrix, like an n by n square matrix, right? So if any random n by n matrix, right, would require like n square entries to store, right? But if you somehow had access to the SVD decomposition, right? Um, to reconstruct, what do you from the SVD decomposition to reconstruct the matrix, what do you know? What do you need? You would need the entries for the UIs, you would need the entries for the VIs, right? And well, and then if you want, you would also need the sigma i's if you really wanted to keep track of everything, right? So from the SVD perspective, n times, okay, so for if it's all like square matrices, like these vectors will have like, n entries, so there are n sums, right? So you need the n entries of the first vector plus the n entries of the second vector plus the n entries of the third vector, right? So you need r times n entries for the UIs. You need all the UIs, I mean, all the UIs. And you would also need n times r entries for all the BIs, right? So you would need n times entries.
You know, why?
Oh, well, right, but I made it square just to keep track. Yeah. It would be otherwise m times r. You're correct. It's just that what makes it nicer if you do it that way is that for the matrix it would be quadratic, right? It would be n squared because and then it's linear in n. That's what I'm trying to emphasize here. That if it's from quadratic, it becomes a linear thing. And then if you wanted, you could also include the single square values, and you would require like those are just numbers, right? So you would require extra numbers for the sigma, and then R numbers or R numbers for the singular values. And by the way, this is kind of like a rule of thumb because there is in this SVD, there's even more relationships, right? Because the vectors are like one, they're orthogonal. I mean, there are other properties. So like, in fact, you could drop the count a little bit, but as a rule, like a bird's eye view, like that wouldn't take away that much more. Like the important thing is that instead of being so in totality, this would be 2n r plus r, right? Right, but it's kind of like if for example, if you do like a truncation, right, or like, I mean, this is not that great if you think that the rank of the matrix is high, right? Because if the rank is basically close to n, then this still kind of like keeps being like n squared, more or less. But if you kind of just keep the larger singular values, right? Like you truncate it, that's also one of the reasons why they do truncation. Or like if for whatever reason it's a low rank matrix to begin with, then this is roughly like O of n, like big O of n. So like you're turning something, from like the storage perspective, you went from something like in principle what O of n squared, like versus O of n, right? So that drops like from quadratic to linear. That's what I'm trying to say. So if the matrix, so matrix is of low rank, or you do like a truncation, right? So low rank, or you truncate it, it's basically you will. This is basically of n, right? Has everyone seen the big O notation? So right. So that's like even again, that's not the most important thing maybe of the FTD because it has so many good properties. But once we go to the tensor train, that's not what the main idea of like doing the tensor train because like decomposition, because the tensor train is kind of like a similar idea. If you had a tensor with a certain number of indices, and let's say like a tensor of with 5 indices, right? And all of them have n possible values, that would be n to the 5. But the tensor train will bring it down to being linear in n. And that's like a tremendous, like, like that seems like a really big difference. Like, again, like there will be something analogous to the rank, right? Which is called like the virtual dimensions. But if you kind of truncate or like keep them that small, then there is an advantage in that. It's kind of like a compression speed. That's what I'm trying to say. Um, In fact, well, yeah, because I guess it doesn't make a lot of sense to start the proof today. At least I'll kind of like show you what the tensor train is supposed to look like so that just we can see this more clearly here. So the idea of the tensor train. So again, I'll show you this how it works next time, but it's like really like a very simple idea. But at least just to kind of like, since we're already starting to talk about the compression stuff. So like I think I had done like a similar picture last time. Imagine that you had like well, actually I'll do it for the case. I'll illustrate how it works for the case of 4 indices next time, because if you kind of like see how it works for 4, like you kind of believe that all of these should work roughly in the same way. If you had a tensor with 4 indices, which I'm going to call I, J, K, and L, right? So the idea is that in the tensor train decomposition, what you will end up having, actually I have the picture here. So yeah, it's going to look like this. Okay, so the tensor train decomposition will be turn into this tensor into a contraction of these other tensors. So if you look at these, like well, these are going to be called the cores. Usually you call them G's, or like, I don't know what the reason for that is, but usually these will call, these are called G1, G2, G3, and G4. Okay, so these are called the cores of the tensor train decomposition. So
again. So those two technically are like same object. So it's like that four-dimensional object. So all of those are like multiplying smaller matrices together?
Yes, they're basically, right. So if the first one, it depends on how you want to think about it. G1 has two legs, right? G1 and G4 have two legs, so they are literally generally matrices in their own right. Okay, so let me just, let's discuss the diagram, what it means in right now. So G1 and G4, right? They are, they are matrices, right? Since they have two legs. And in this case, G2 and G3, they are at order 3 tensors, right? So, uh, order 3 tensors. Okay. Uh, but so if we have kind of like an analogous thing to matrix notation, right? Of matrix multiplication, this is saying is kind of like the tensor train is kind of like this matrix times this tensor times this tensor times this matrix, right? So it's kind of like a decomposition of that sort. The reason why I'm using the word tensor train because it's kind of like more suggestive, of the train with like kind of like all of like with like a combination like you see on the train. Like the reason why it's called like the matrix product state is that if you think about giving like specific values to the free legs, if you give a particular value to I or J or K, then it is really more like a multiplication of matrices like in the middle because those are just legs that are being added over. So that's why I'll mention this more precisely next time when I show you some examples. But you'll see literally multiplication from matrices because you imagine that the free indices, like you give them some specific values, and then that like just leaves like the virtual legs. That's how they're also planned, like for the virtual funds, like being some open. Yeah.
Why matrices and not also?
Oh well, I mean, if you what you repeat that kind of
If you connect G1 and G4, so they're also regular, that's it.
right, no, but like if you mean like kind of like
Yeah.
well, first you could only contract them if they have the same number of indices, right? Like if I and L take the same number, but also they're like then it's like a different thing that you are doing because the tensor itself does have 4 free legs for free indices. If you kind of contract these two, then that wouldn't be true altogether always because like you're only left with something that has 2 free legs. So like that would be a matrix, right? So you do want something, you kind of want some kind of like conservation of free legs that are like, if you want to call it like something like that. If you have on the diagram on the left side something that has 4 non-contracted legs, you need to have something with 4 non-contracted legs on the right side. What I'm saying is that if you, which I'll show you next time, if you give particular values to I, J, and K, right? Like imagine like I don't know how the computer works, but memory storage. If you're kind of calling the entry 1111, right? So this you said I to 1, J to 1, K to 1, and L to 1. So this is being takes value 1, 1, 1, 1. Then there's only one releg here, which would be like a vector. So it's kind of like a vector times matrix times vector, right? So except for the beginning and the end, there's mostly like just matrix multiplication in between. So that's why it's called like a matrix product state as well. Because I mean, this is not specific to a tensor with 4 indices, right? Like if you had 1, 2, 3, 4, 5, it's kind of like the same. You'll see once I show the proof next time, you'll see it's kind of like the same idea every single time. It's really fun. So you always start with kind of like and begin with something with just 2 legs, but in the middle you always connect by 3 legs. No matter the number of entries no matter the number of indices of the original tensor. So you could have had 10,000 entries or 10,000 indices, and in the middle there's always 3. And that is where you see the compression advantage. Like if you kind of like think about it, because if you just do like a count, then maybe let's say that would be the last thing I mentioned today. But if you imagine that just to make your life easier, that the number of values each index can take is n, so that it's kind of like a cube, like a hypercube, right? right? If the number of values for ij and k, oops, sorry, this could have, and L is n, then T would have required n to the 4 entries, right? Then T requires n to the 4 entries. Okay. And again, we'll see the details next time. These, like the number of values this can take is kind of related to the ranks of SVD decomposition you do. Well, let's say that they're bounded by a certain number, which I'll call P for now. So if I'll just give them these numbers, like these legs, some names so that it's a little bit easier to keep track of: alpha, beta, gamma. And let's say if alpha, the number of entries for alpha, and the number of entries for beta, and the number of entries for gamma is maybe not always the same, but it's always less than some power d, then some number d, then how many entries do you have on this diagram? You would have n times d, like so you get on the right hand side n times d plus n times d squared, right? Plus n times d squared plus n times d, right? Because each of these puts an n factor, and the others just depends on the number of entries, the length of the virtual legs. And so is that so it's basically like O of n d squared, right? So this is kind of like O of n d squared. And again, that is great if you can control the d's, right? So how can you control the d's? For example, if you decide to do like a truncation or other, schemes, then you can kind of keep it low, but low value for d. So it is a tremendous gain of going from n to the 4 to be something more or less like linear. Well, it is still linear in d. I'm just saying, like, sorry, it's still linear in n. It's always linear in n. It's just that if d is too high, obviously that wouldn't, be that much of an advantage. But if you somehow can make the d not that high, like not depend on n, right? Like so that it doesn't become like a chicken and egg thing, then you can. It does give like a tremendous compression speed. So that's kind of really nice with all these things. It is really cute. And then and it has a lot of applications for teams, like every scheme where you have to do kind of like an approximation of a continuous function or something like that, like for numerical analysis where you have to, like use like a grid or something like that. I'll give you some examples like on Thursday as well and show you how it works. But it's really kind of like the diagram that I had mentioned at the beginning. We start with the tensor. I can even more or less explain it verbally now. You start with a tensor. You pretend that these 3 legs form like a multi-index, like a single index, so that it looks like a matrix. You apply SVD to that matrix. You keep the U factor basically of that initial SVD. You turn the other D matrix into a new tensor. Then you kind of keep going, like, so it's kind of like a back and forth between doing SVD, converting the matrix back into a tensor, but with a fewer leg, and so it's kind of like a dance with SVDs and tensorization, matrixization, or whatever it's like. That's called. Okay. But yeah, let's finish here, and then Thursday I'll tell you how like the details on that, and then hopefully next week we can start doing some applications involving this thing. But yeah, I can still stick around if someone wants to talk more about this.
Predict you probably didn't see it, but I finished the assignment for, you have a Mac, right?